So hello guys, welcome to a new video. This video is sorry for the background noise because it is raining today. Okay. Today is the first lecture of MTB. So first let me show you the question. You can get the question here. There is the booklet MTB, and you get the booklet clicking here, and this is the MTB as you can see, and you get also 2 hours for it. Same configuration, 8 questions. First questions, let's see. So the first question here is saying A, B are two linear maps. I will recommend you to please take a screenshot and then follow along my next subsequent parts of the video. Okay, otherwise you will forget what was the question and it will be difficult to follow along. So it is better to keep a screenshot and take it. But if you want, I can make a split screen, but it would be a little difficult for you to see if you are looking in the mobile to view the letters, so I am not doing the split screen. Okay, you take a screenshot and follow along. Okay, so that is good. Now you have two linear maps A and B from Rn to Rn, and M be any natural number. A is not identity, A is not 0, and A is a projection map. That is A equal to this A square, this projection map, and A and B is commutating. B is a nilpotent of index m, so we have to prove that b to the power n minus 1 is 0. Now if b is a nilpotent, we know b to the power n must be 0 because this is n dimensional, n cross n matrix. That is very simple, you know. But b to the power n minus 1 is 0, but we have to prove. Okay, so let us try this. Okay, so first that we can go along, what we can say about a projection map. First we have to understand what we know by rank nullity theorem for any matrix. For any matrix, say A, by rank nullity theorem, what we know? Rank of A plus nullity of A equal to dimension of R power n, as A is from Rn to Rn. So, and now another thing is that image space of A intersection null space of A is here only 0. Why? Take any vector from image of A intersection null space of A. Okay, null of A means null space of A. Here we am denoting. So image of V belongs to this means AV equal to V. You all know by the projection map property. You know, right? AV equal to V if V is in the image. And why this is true? Okay, let us see why this is true. Because look, as V is in the image of A, then this means there exists a V dash, say, belongs to Rn such that AV dash equal to V. And now operate both sides, A square V dash equal to AV. Okay, but as you know, what A square means A, so AV dash equal to AV. But now what is AV dash? AV dash equal to V, so AV equal to V. That we have written. Okay, nice. Now again, as V is in the null, So AV equal to 0, so that you give V equal to 0, or precisely write like that, 0 equal to V. That means only vector in the intersection we get V equal to 0, so intersection is 0. Okay, so that is the whole follow along. So together with this 2 and 1, so from 1 and 2 what we can write? That Rn is nothing but image of A direct sum with null space of A. है कि नहीं? क्योंकि इमेज और नल स्पेस का जो भी है इंटरसेक्शन में 0 है, मतलब दे आर बोथ linearly independent spaces and their dimension together make up the whole dimension of Rn. So any vector of Rn we can write using the basis of image of A and null space of A, because total basis count is the whole basis. So that is what is the direct sum means. Okay, yeah, that's it. Okay, now now you tell me what we can think of. So you can prove it that any vector of Rn can be written as in a basis of image of A and null space of A, because using their basis, the total if we add the basis number of basis elements here and here, they give up make up the whole space in and in. So basically using the vectors basis of together, taking the basis of image of A and null space of A, then we combine their basis, they will be linearly independent because their intersection is only 0, and hence they form a basis of Rn, and hence using their basis we can write any vector. So that is the main thing of the direct sum. Okay, so that is what it is. So this is because of the property of projection map. Okay, fine. Now what we will do, and here is an important thing to remember. So let us consider that image of A, the dimension of image of A, let's say this is R, and dimension of null space of A, what would be the dimension? N minus R. Now here is the important, what is R? R should be greater than equal to 1 and less than equal to N minus 1. Now you will argue that why it is cannot be N, R cannot be N. Important, R is not equal to N and R is not equal to 0. Why? If one by one we will see. If R is equal to N, then what will happen? The image would be of dimension N and nullity would be 0, right? Null space would be 0. But if null space is 0, that means A is a bijective map. But if null space is 0, and you know A is diagonalizable, every projection map is diagonalizable due to its minimal polynomial splits into what? Minimal polynomial is splits into single degree power, I mean linear factors. It is diagonalizable if it has no, or and it has only eigenvalue 0 and 1. but as it is your nullity is 0, that means no eigenvalue can be 0, then all eigenvalues are 1. If you diagonalize, you get all 1, means this is the identity matrix. But what is given? A is not equal to I. Okay, if you can remember. So that means R cannot be n. Okay, so contradiction. Similarly, if R equal to 0, then what happens? Then image would be 0, right? And image 0 means nullity is full. That means all eigenvalues are 0. That means A is a 0 matrix, which is also contradiction. But right, so together we get R cannot be 0 or neither R can be 1. So that is R is in between this, which is really very important to prove. B to the power n minus 1 is 0. Okay, so in the big later cases. Now given AB equal to BA, okay, what is given? AB equal to BA. What that means? B of image of A is image of A. That is, image of A is invariant under B, and kernel of A is invariant under also B. Why? Let's see. So let's prove this. Okay, this is claim. Let's prove. Now take V belongs to image of A, and we have to prove BV also in image of A. So BV is equal to what? B A of V dash, or you can say A of V actually, sorry. But B A of V means A B of V. Then what that means? BV belongs to image by the property again, because BV is a vector which is invariant under ABV equal to BV. So proved, it is proved that B is inside this. And again, let's say V belongs to kernel of A. This is also very easy, because then BV would be what? We have to prove BV is also kernel in the kernel. So ABV, it has to be proved to be 0, but ABV equal to BAV, but B of 0, which is 0. So again, BBV becomes in the kernel of A. Okay. So we have proved these two easy fact. This is due to the commutating nature of A and B. Okay. So by this thing, what we can do, we have Rn equal to image of A direct sum with kernel of A, or sorry, nullity of A. So null space of A. So we can use this and this basis to write the B, okay, in that basis. So let's say B is in that basis, or basis taken from this and this. So this would be B1 and B2, and this would be 0 and 0. Why this is? Because using the basis, if we multiply B, it will be inside those elements. So this and rest of these things are 0. And again, if we take basis from this, and this image part is 0, and if we multiply it, this would be inside the basis element. So the image part would be 0, and this part would be kept, right? So B in that basis would be of the form B1 B2 in the diagonal form. Okay, that is the beauty. And now, as B to the power m is 0 given, as you remember, so similarly B1 to the power m is 0 and B2 to the power m is 0, as you know. In that form, if you multiply B to the power m, that would be B1 to the power m 0 0, B2 to the power m by the diagonal form. But now it is 0, implies both this thing. Okay. but rank of dimension b1 is what is the what is the index of b1? Index means what is the size, or you can say size of b1. So for more precise, size of b1 is, what was b1? b1 we taken as the image, no? So image dimension of the image we taken as r, so this is r, and size of b2 is n minus r. Maybe you can say this, right? So this generally implies that it is nilpotent, right? So it must be what? b1 to the power r is 0 and b2 to the power n minus r is 0. Okay, so what is the nilpotency then? Nilpotency of B is simply maxima of r and n minus r, है कि नहीं? क्योंकि देखो अगर इन दोनों में से n माइनस आर मैक्सिमम है तो n माइनस आर पुट करने से दोनों ही जीरो हो जाएगा, तो b जीरो हो जाएगा, तो हमें मैक्सिमम लेना है। पर इन दोनों में मैक्सिमम क्या है? n माइनस वन है, क्योंकि r ranges over n minus 1 to 0. So if you range this, you definitely understand the maximum of r and n minus r must be n minus 1. It cannot be n anyway, because r cannot be 0. So r can be 1 at the least. If your r is 2 comma n minus 2, maybe something, but maximum is n minus 1. So b to the power n minus 1 is 0. Basically maximum is 0, but b to the power n minus 1, I mean we can say less than equal to n minus 1, and so obviously then b to the power n minus 1 must be 0. So this is the actual proof, you can say. So yes, the proof is done. Now you can revise it, and I would comment something here. You can think of why it happens. I mean, yeah, this is true, but that means what? Eigenvalues of b1 and b2 are all 0, which implies they are nilpotent matrix, and you can prove for any nilpotent matrix the characteristic polynomial is always, because all eigenvalues are 0, so characteristic polynomial must be x to the power the dimension, that's the size actually, x to the power the size. So that's why b to the power r must be 0, because there is no other zeros, no? So the characteristic polynomial must be that. So by the and every characteristic polynomial is, as you know, by the Cayley-Hamilton theorem, matrix satisfies the characteristic polynomial, and that's why it is. Okay, so yeah, characteristic polynomial is the roots of the characteristic polynomials are the characteristic values, and you know the characteristic values are all 0. So yeah, so yes, that's it. So next class we will do the question number 2, which I am just showing you, is find the distinct group homomorphism from Z6 to symmetric group S5. That you just see in your mind how you can approach it, and the next class you will see. Thanks for watching, and obviously I will upload the classes and you will get them one by one here. As you can see, from question 8 is done. Now MTB and then all other part you will get one by one from here. Okay, so yeah, या यू कैन सी दैट आई कैन मेक, मतलब मैं बना सकता था कि एक और फोल्डर बना देता MTA के रूप में, और MTB तो थोड़ा अच्छा रहता, पर ठीक है, मतलब फिर बहुत ज़्यादा फोल्डर नेविगेशन करना पड़ता, इसलिए मैंने वो नहीं किया। बाकी 1 बाय 1 सब इधर मिल जाएगा, तो आप लोगों को कोई दिक्कत होने वाली बात नहीं है। तो ठीक है, थैंक्स फॉर वॉचिंग।